This video is about the fundamental theorem of algebra and complete factorization. For our notes, we'll start with the fundamental theorem of algebra, which states that every polynomial, defined most generally by the just definition of a polynomial where the leading coefficient is a sub n, the highest degree is n, and then it goes on down from there in descending order. Of course, the constant term can be on the end. We're going to assume that n is greater than or equal to 1. Our degree has to be a whole number. And then a sub n, the leading coefficient, is not 0. Well, if it has complex coefficients, recall, complex numbers are defined as a plus bi, where a and b are real numbers, but then the presence of the I potentially means you could have an imaginary piece to it. So complex encapsulates all real and imaginaries. With complex coefficient has at least one complex zero. We've been working a lot with zeros lately. This theorem is just guaranteeing that we'll find at least one for any polynomial of any degree. The complete factorization theorem states that if p of x is a polynomial of degree n greater than or equal to 1, then there exists complex numbers, a, c1, c2, all the way up to cn, with a not equal to 0, such that the following is true. We can write p of x, our polynomial, as a, the leading coefficient, times any number of factors of the form x minus c1, x minus c2, all the way up to x minus cn. There could be n such factors. Significantly, this theorem is stating that we can take any polynomial, p of x, and write it in factored form. Yes, that means that any polynomial can be factored. Now, that may seem a little strange if you think back to the days of learning factoring methods. There were some cases in which you may have seen a polynomial and stated something like not factorable, or you might call it prime. And that was true in that context, but this theorem is saying that there's a way to power through it and factor it completely, but you'll note that complex numbers may be the result of doing that. In other words, there may be no way to do it with only real numbers, which is probably when most factoring methods are being taught, which is why you might have to say at some point not factorable. But when complex numbers are in play, there is a way to force through it. Let's try an example where we find all zeros, keyword all here, of the following polynomial, and notice it actually specifies real and complex, then factor it completely. Well, our polynomial states f of x equals x cubed minus 8. Now, at first glance, you may recall that x cubed minus 8 is actually one of our standard difference of two cubes. We can just put a quick note about that. Difference of two cubes, which means, as you may recall, there's a formula that would help us factor this polynomial. So let's go ahead and apply the formula. If f of x equals x cubed minus 8, then remember the first term is really like an x being cubed, and the second term is really a 2 being cubed. And the formula for factoring a difference of cubes would state that we say it in the following way: x minus 2 times x squared plus 2x plus 4. So again, you may need to review the difference of two cubes factoring formula. It's very similar to the sum of two cubes, but that formula would state that we can factor the difference of cubes we're given at the beginning into what we just wrote, a binomial times a trinomial. Now, this is where things get interesting. In the typical factoring methods, you may look at this trinomial that's lingering here at the end of what we have, the x squared plus 2x plus 4, and say, okay, well, it's a trinomial. Let's try a three-term factoring method for it, such as guess and check or other various methods to factor something like this. But you'll find quickly that there's actually no way to factor this according to those methods. In other words, we would usually stop right here if we were just trying to factor this original x cubed minus 8 according to all basic factoring methods. Well, now, using our theorems, we're going to power through it and say, well, okay, fine, there may be no more real number ways to get through this, but what about an imaginary or complex way. And so to get there, we'll actually take this trinomial and apply the quadratic formula to it, which would state that x equals negative b. Okay, b is 2 here. So negative b plus or minus the square root of b squared, that'd be 4, minus 4 times a, which is 1, times c, which is 4, all over 2 times a, which is 2 times 1, or just 2. Now let's reduce this a step or two here. So we'll say negative 2 plus or minus the square root of, now this inside the root we have 4 minus 16. So we should really say negative 12, and that's all over 2. We're going to keep reducing this as we would have in the context of solving quadratics with this quadratic formula. And we'll write this as negative 2 plus or minus. Now remember, this negative sign underneath the root could pop out as an I for the imaginary unit. And then 12, if we split that up, 12 is really 4 times 3, and the square root of 4 would turn into a 2. So really there's a 2, and then the 3 would be left under the root all over 2. So really we have, again, negative 2 plus or minus I times 2 root 3 all over 2. And then we can simplify a little bit because there's a common factor of 2 in all terms of this. If I divide all by 2, I'll end up with negative 1 plus or minus I root 3. All right, so let's back up and find out what we're doing here. If you go back to where we were, we started this quadratic formula from the trinomial factor that showed up in our difference of two cubes factoring process, which again, normally we would just stop right there, but now we're saying, well, let's keep going and force our way through it. Notice when we used the quadratic formula, we ended up with complex and even imaginary roots here. And so we're going to use that in our list. If you go back to our original problem, it said find all zeros of the following polynomial, real and complex, then factor it completely. So we've now found all the zeros. We just have to write this in factored form. And so we'll say here that f of x equals x minus 2. That was the first root. We knew that one directly from the difference of two squares factoring formula. But then this trinomial that we split up, we have to put together here using our theorem above, which states that x minus c, where c is the root, is how we're going to write this in factored form. Now the c values for this trinomial are what we found using the quadratic formula. There are 2 of them. So we're going to write each one carefully. So x minus, I'm going to put one at a time. We'll say negative 1 plus I root 3. That's one of them. And then secondly, we'll say x minus, and then negative 1 minus I root 3. That would be the second one. So the plus or minus is showing up as 2 different options. But now what you're seeing is the fully factored form of our original polynomial. The reason this doesn't normally show up when you're learning factoring is, again, because we have imaginary roots that showed up here. So we'll simplify this one more time just to distribute some of these negatives here and write our final answer as x minus 2 times, if I distribute this negative in, I'll end up with x plus 1 minus I root 3 for my next factor. And then lastly, distribute the negative as well there to get x plus 1 plus I root 3. And this is the final form in which we'd like to leave it. So we found the roots of this polynomial, and we use them to factor it completely. Of course, completely means a lot more than it used to now that we're okay with complex and even imaginary roots.